everybody, how's it going today? I'm Jon from the Alienware Community Team, here with Anna, my co-worker who is also from the community team. How's it going today, Anna?
It's going well. I'm very excited to be here. I'm also not highly caffeinated, so we're going to be doing well.
So we've got a really fun and exciting thing to get started for everybody. This is the first episode of a new show that we're going to be doing regularly called the Alienware Transmission, which is kind of a new idea that we had when I started on the team over here. So Anna, why don't you tell us a little bit about what we're going to be doing going forward with this?
So we wanted to do a bunch of different things. In the past, we've done Discord Q&As. Those won't be going away. We've done Reddit AMAs. Those also won't be going away. But we wanted to do something that was a little bit more interactive that we could also share on different platforms, as well as answer all your guys' questions. Because let's be honest, that's, you guys are the reason we're here.
Yeah.
So
and you have a lot of questions.
A lot of questions, which is fine. But that's why we rope in other people to answer them for you.
Yeah, so as you can see below, there may be some other faces, some more familiar than others. We have our post-celebrity Travis North, who's been on camera before, and we're going to try to embarrass him before we get started here by talking about his celebrity status. Travis, do you want to let everybody know what you do with Alienware and Dell?
Yeah. Thank you, Jon. So my name is Travis North. For those of you that don't know me, basically I work in the office of the CTO. My expertise is basically thermal power, acoustics, and cooling. You may have seen me before on PC World. We've done interviews before where we talk about basics of heat transfer, why we do what we do. And my job within Dell is basically to enable our systems to maximize performance, to give you the best gaming experience possible within the constraints of the system. So any technology associated with fans, heat sinks, cooling, control, that is my domain. Happy to be here, and we'll hopefully get the questions answered that you guys have for us today.
Yeah, we've got a few.
Thanks,
and we
Jon.
went over them to let you know a little bit ahead of time. So we're not getting Travis right off the cusp, trying to get him to go through kind of complex engineering answers right away.
We were a little kind this time.
We're a little kind this time, but we also...
Next time, it's the gauntlet.
We also have Mark Gallina from Intel with us. So Mark, do you want to explain a little bit what you do at Intel as I tried to squeeze in your job title into that little box there?
Yeah, thanks, Jon. So Mark Gallina, I'm a principal engineer in Intel's client computing group, and I'm like Travis, my focus is on heat transfer, although my team and I work more on the CPU itself. So we do a lot of the early engineering work as Intel designs the CPUs, and then we provide that information to Travis and his team so they can make sure that the CPU, when it gets put into the system, is adequately cooled at the right skin temperatures and acoustic levels and things like that. And we'll get into a lot more detail of what that means as we go further in the conversation today, but I'm excited to be here and really happy to answer questions from the community.
Yeah, and I'll warn everybody, we will be getting into a lot of detail, so we'll try to make sure that everything's clear for everybody, whether or not
I'll try and keep a high level.
Yeah, Anna and I will come in and explain kind of the stuff at a normal level, and then these guys are going to try to explain at the engineering level.
Jon, we're not that bad, I promise.
No, they're good. So I'm teasing. No, they're good. A lot of fun here.
We don't have any whiteboards behind us. So
no, but we do have diagrams.
Oh, that's true, you do.
I was going to say, doesn't he?
Awesome. So also just as a warning for everybody, I will be honest, this is our first time running this show. So if there's any technical issues from me not doing the production properly, I apologize in advance, but I think we should be good to go here. But before we dig into the meat of everything going on, I do have a few little tidbits that I want to do some announcements for. So while we move over to the news, the first thing we actually want to announce, and this is the first place anybody is going to be hearing it, is as of July 19th of this year.
Happy birthday to me.
Yeah, on Anna's birthday.
My birthday gift to you.
Is that we are going to be releasing XMP memory from Kingston Fury on the R13 Aurora. So that's really cool news. We have that coming because previously our memory had been the stock memory with the Intel specifications, which if you're not aware, on DDR5, RAM runs a little bit differently than it did on previous versions like DDR4. So the more sticks you had, the lower frequency your RAM had to run on. With XMP, we can actually enable it to run up to 4800 megahertz across any number of RAM sticks you have in your system, whether there's 1, 2, or 4. So that's going to be really exciting as long as you have those XMP profiles available, and you'll be able to purchase them starting on July 19th. So that's going to be really exciting for us, and I can't wait to see what people are doing there. I haven't got my hands on any of it yet, and I can't wait to because I love the XMP memory there.
And where can you find these Kingston Fury XMP memory?
They will
to
be on
purchased?
the product page starting on the 19th. They're not available yet. So we'll be linking in the show notes, which you'll be able to find on alienwarearena.com after the show. You'll be able to see our show notes with all the different topics we've talked about and a summary of what went on. And we'll also provide the link in the description on the YouTube channel after we go live. But then there is some other news, but I can only share a little tidbit with you. But also happening on the 19th, we have some really, really exciting news coming to our laptop families. So make sure you follow into our social channels, follow us on Arena, check out Twitter, all the fun things, and there'll be a lot more there. No spoilers today. I'm sorry. I tried to get permission.
Can I give like half a spoiler?
No spoilers at all.
But like, it's not a thing spoiler. It's I've been busy.
Yes, Anna has been very busy working on things. We can say that. But
that is all I will say.
That is all we will say. So make sure you check out our Twitter channels, Facebook, Instagram, Arena, everything, anywhere you can find Alienware. Make sure to check that out later, and you'll be able to find out what's going on the 19th. But that's all I have for kind of the product updates and the news here. So now why don't we dig into all the fun things that we want? We brought Mark and Travis here to talk about. So Travis, I'll start with you. You gave us a high level understanding of what you do with kind of you work on the thermal systems, but can you dig in a little bit more about how that relates to the game experience? When you're designing a system and the thermal understanding of that, what actually does that mean? What are you looking at?
Yeah, great question. Any system, right? Mobile, laptop, desktop. When we start from it, basically we start from a piece of paper, and we really have to focus on the experience. Like, what level of acoustics do we expect for that system to operate at? Then what is the expectation for performance? Is it, hey, 3D Mark from a benchmark perspective? Is it VR Skyrim? Is it League of Legends? Is it Heroes of the Storm? Whatever the application is, we have a list of applications that we use that we actually benchmark, and then we use that information to set the power conditions that we want to operate to. Where Intel comes in, basically Mark's team and the rest of his team is responsible for giving us those requirements. Then once we have those requirements, which is power, what we call T-case, which is literally the temperature of the case or the temperature of the junction. Once we have that data, we can build out the entire system. That is basically what dictates how big the cooling solution needs to be. So if you look at like our Alienware mobile products with the quad fan solution, where we've got multiple fans and we've got heat pipes wrapping around the entire structure, we've got one of those fans positively pressurizing the system. All of that is done at the end of the day to cool those components to meet the performance experience that we want from an acoustics, power, skin perspective, and even from a cost perspective from the platform itself. But good question, John.
So, and when you say skin perspective, just so everybody knows, what do you mean when they say a skin perspective in a laptop?
I was going to ask that. Thank you.
Well, from a skin temperature perspective, so I was using slang, which I probably shouldn't have done. At Dell, we have done probably over hundreds of hours of usability studies where we see how people interact with the system. Do you lay your hands on the palm rest left and right? What do you like from a temperature delta, say from one palm rest to the next? Let's say you're playing hardcore gaming, QWER keys, which are your primary gaming keys for like...
Or WASD if you're not playing.
Yeah, there you go. Whichever one you want, right?
I was hurt a little bit there.
The core keycaps that you focus on gaming, we have a particular focus on those areas. The ribbing between the keys, what we call the strip cover, which is above the keyboard, the D cover itself, we have fine-tuned our skin temperature specification for every single one of those regions. So when we know that, hey, you are playing League, a first-person shooter, whatever it is, we have optimized that system for that particular experience. And we do this per line of business. Hey, is it the top-end Alienware systems all the way down the stack to the more valued system itself? All of those are tuned based upon those specific experiences, from skin temperature to acoustics to performance.
And to jump in a little bit, and we'll go a little engineering on you guys here. The reason skin temperatures become a very critical thing for our mobile systems is when you put heat inside that small box, it goes everywhere. Right. Yeah. So even though we've got all the fans, we've got the heat exchangers, we've got the heat pipes, those bring the majority of the heat to the ambient, which is where we want the heat to go. But there's nothing, it's still going to conduct up through the system. So it's going to get to the keyboard. It's going to get to the bottom channel, the D panel that Travis mentioned. That's the bottom surface of the laptop, right? So if you have it on your lap, that's what's touching your legs. But no matter what we do, the heat's going to go to those surfaces. And so the amount of heat that goes there, the ratio, that's somewhat fixed based on the total design of the system. And so that does end up being one of the critical parameters we pay attention to in terms of the total system power that we can handle.
Okay, that makes a lot of sense, that you have to kind of focus on the whole aspect instead of just, because when we think about, and when I think about cooling a lot of the time, like I think about CPU temperature and I think about those specific components versus thinking about how hot the unit is to the touch. But it makes sense that is a... Maybe
I'm different, because to me, that's exactly what I thought of. I have an X14 that I lay in bed.
Yeah.
I play games on. So to me, like, you want to make sure that's not hot, like on your legs or on the blanket, which you shouldn't put it on.
Don't put your laptop on don't put it on your blanket. Anna,
don't do that. Don't do that.
Don't do that. But we have sensors that we can detect when you're doing that, and we can adjust performance optimally, right? So we have gyroscopes that we can actually see if you're flat on a table or not. All of that data actually comes into play when we're optimizing a system. So we've thought through a lot of those scenarios, and every single component, from memory to CPU to GPU to storage devices, all of those have been tested, and we control to those temperatures to optimize that system basically under any condition. So if you're at high ambient, you've throttled the system, let's say you've choked off the airflow, we have safety features through, actually some features from Intel called their dynamic tuning technology that we use to optimize that system to ensure that you're going to be safe, you're going to be operating within spec, and you're going to reliably give the performance that you can for that specific condition.
Awesome.
But that being said, don't block.
I didn't even know that.
Just don't do it. Just because you can doesn't always mean you should.
Yeah. We do a lot of work to make sure.
You know what I'm doing? I'm helping testing for future systems. I just the hotbed of destroying things.
Awesome. So then we kind of know what Travis does, and it sounds like Travis is saying too, like you get instructions from Mark's team at Intel about when you're designing the system. So not to give Mark too much credit here, but it sounds like he's kind of controls what Travis can do. So Mark, I know, I love teasing these guys off of each other. It's really fun. But we already heard the Heroes of the Storms jokes, because Mark, Anna, and I loved Heroes of the Storms until it recently kind of got decommissioned. Yeah. And Travis has just been making fun of us about that. So Mark, when you want to tell Travis what to do, what do you do in your role, kind of with from the Intel side?
Yeah, so from the Intel side, so remember when Travis was saying he starts off with the blank sheet of paper and they work through what does the system look like, how big is the chassis going to be, what are the games or other workloads that want to run on it. Everything eventually runs on the CPU itself, right? And so we have to figure out how to get the heat out of that die into the ambient air. That's where we move all the heat to. And so the shape of the die, the layout of the different parts of the die that dissipate heat, and we'll get into those in more detail later in the talk, but the way the heat transfers or conducts from that die up through the heat exchangers and into the airflow, that's all dependent on the design of the SoC itself. And so what we do is we do a lot of work early on to give the information to Travis and his team in terms of, here's what to expect. Here's where the heat's going to be dissipated on the die. Here's the areas of the die that you really need to care about. Here's how much power you're going to need to worry about for the different types of workloads that you're really interested in. And so there's a couple things that we can do. We can give it to them in terms of absolute thermal resistance, which is the ratio of how much temperature you're going to get for a given power level, as well as here's what you can do and expect for the next generation compared to the previous generation, right? So if you've got a chassis that's already designed and you want to put the next generation Intel CPU in it, here's what you would need to do from a fan speed perspective or a heat exchanger perspective in order to make that work.
So I guess basically you guys have a very close friendship is what you're explaining to me about the amount of times you guys, well, one, have ribbed each other off stream, and then two, for the amount of times you have to talk together to make sure, everything works out.
I would push it that far. There's official documents that are actually transmitted from Intel to Dell. So
my bad. Okay, I was hopeful that you guys grabbed a beer on Friday nights and were like, okay, so this is what's going to happen coming up next week.
I wish it was that easy, but yeah. But I mean, to put it in perspective, right? He mentioned thermal resistance. At the end of the day, the physical size of the cooler, how big the fan is, how much airflow, right? If you put, liquid nitrogen on a system, it's a very cold substance. It has a great heat transport capability. All of these things that we are looking at really come back to the silicon and what Intel's doing to basically provide the engine. You can think of the CPU as the engine in the car. We, Dell, are packaging the car around the engine. And so we're doing the transmission, we're doing the steering wheel, the aerodynamics, what it looks like, the lights, the stereo as an example. All of that is Dell, but the core heart of the car is the engine, which is Intel.
Awesome. And then so Mark also mentioned, and Travis has mentioned, kind of the specific workloads in play. And Travis, you said something along the lines of delivering like the best gaming experience. When you guys are talking about thermal design and how you're coming up with answers to those kind of problems as they come up, when you're talking about different workloads, what does that mean? What are you talking about? How does different workloads make different demands on the thermal dynamics of a system, things like that?
It does. I'll take a first stab at this, then Mark, maybe you can chime in. So when we talk about workloads, typically at Dell, we characterize what a customer's doing. So how are they running, and I'll just use my favorite game, right? League of Legends with Discord, while they've got Chrome up with, say, streaming audio, or maybe they're live streaming from a separate system, right? We actually look at all those different type of modes that the customers use those systems, then we characterize it. We can go in and look at power on the CPU, power on the GPU, power on the subsystems. Then we characterize those workloads. And typically what you see is we work to optimize those systems. And so from a mobile perspective, concurrency is critical. How much energy do I give to the GPU versus the CPU to ensure the best optimized system or the best workload? For example, if you're running a GPU intensive application, it makes little sense. It actually can hurt you if you allocate too much power to the CPU. You want that power to be able for the frames per second, the frame rate coming from the GPU, and you want the CPU to have just enough power to feed the GPU. And this is where this comes into play. It's a fine dance between those 2 points. Now, Intel and even some of the GPU providers provide us tools that we can to optimize those workloads at runtime, but the cooling solution in the system dictates how much capacity I have, and then it's up to the control of the system to optimize that capacity at runtime. So if you're doing most games that we typically see, it's about a 5100 loading. A lot of times you'll see 50% on the CPU. It can be 80 to 100% on the GPU. VR is kind of an odd one. As you start doing, let's say you've got an HTC Vive Pro and you're doing Skyrim, that can be much more intensive. And so we actually have a good characterization of all these different workloads. And then based upon the system, we design the cooling solution with feedback from Intel. What do they need to run their CPU at, and optimize the size of the cooler, the size of the heat sink, and the system itself, from battery sizing, memory capacity, voltage regulator. All that's done to optimize for the workload.
And so
I'm gonna interject here. Is there a way for those who might not understand exactly all of that terminology? Is there like a little surface level example you could give us by chance?
Yeah. So if from a CPU, well, Mark, why don't you take a stab at it, then I'll come back, because maybe you can explain it a little better.
Travis passing it off.
Yeah, I didn't see that bus coming. All right, so let me take a shot. So when you're looking at the CPU itself, right? We've got different cores, which we've talked about is in our newest generation parts. Like we have more cores, so the work gets partitioned up onto the different compute domains that we have available. And so the big question is, when you have, let's say Travis has designed a system and it can support 100 watts total, and we'll just use 100 watts because now the math is easy, right? So out of that 100 watts total, like some portion of that needs to go to the CPU for the compute cores, and then some portion of it needs to go to the GPU. And if we use the ratios Travis was saying, we would say, okay, roughly 30 watts of that goes to the CPU, 70 watts of that goes to the GPU. Right now, the question becomes, as you're going through that game and you suddenly turn a corner in the world that you're exploring, and now it has to render a whole new scene, right? That data needs to get from the CPU to the GPU. So now suddenly the cores need to do a little bit more work, so they might jump up a little bit, right? And so we're constantly trying to balance the total power budget between all the compute domains within the system, so we stay within that 100 watts that we have total, in order to give a nice smooth frame rate, a good user experience overall.
And that 100 watts is also just an example to make the math easy. It's not saying there's only ever 100 watts. Just in case anybody is listening and they're like, there's only 100 watts. No, that's just an example to make the math easy for everybody to understand there.
Yeah.
No, we're much higher than 100 watts.
Yeah,
I can tell you that.
we're way higher than that a lot of place now. So when you're talking about kind of developing like a cooling solution that ties directly to the workloads that they're intended for people, is that to say sometimes like you may see that maybe a system designed for rendering video at 24/7 or doing CAD work is going to have different kind of thermal solutions than a gaming system because we expect kind of the GPU to have more power needed a lot of the times. Is that kind of what you're explaining there?
You can, right? So the question comes down to is how much cooling capacity do we need for those specific workloads? So let's say someone is CPU focused, right? And then the heat pipe placement, the fin stack placement, the fan placement, we would optimize off the CPU for that particular use case. Similarly for the GPU, but we actually balance both of those. We actually come in early in the system. We get the feedback from Intel. Let's say we just use NVIDIA as an example for a specific GPU. We get the requirements. Those requirements would be power, temperature, thermal resistance. Then off of that, we build out that system. So every system that we tune, and that's the great thing about Dell, the reason we have different product lines, those product lines are typically optimized for those specific workloads. If you want corporate type environment, right? Excel, Word, PowerPoint, etc., that's Latitude. If you want high-end, say, precision workstation applications, CAD, CFD, FEA, even some rendering, right? So video editing, that's Precision. Gaming, we are very focused on GPU capability and CPU. And so ensuring the threads from the CPU can feed the GPU, and then we have it optimized for the workload at hand. And that all comes into play from turbo performance, how the temperature responds from the CPU, to basically acoustics. And if it's a laptop, skin temperature. And if it's a desktop, it could be power from the power supply, and optimizing all of that at runtime.
Awesome. That makes a lot of sense there. And then from that kind of question, the other one, I think you mentioned it already. I know we've mentioned it like 8 times when we discussed him, but TJ control. What does that mean? Can you just explain that? Just teach me.
Okay. I think, I'm going to give you
non-engineer terms.
Non-engineer terms. I'll give you the Dell version. Then let's let Mark talk to this in a bit, because I think this will be great for Intel to talk to the history here and what it means. The CPU temperature is important from a reliability standpoint. And so as the power is going into the transistors, they're flipping, it creates heat from friction. It comes out of the system itself. And we have to keep the temperature of the die within spec to ensure it can operate over the life of the product. And historically, we control to a TJ max. So when Intel gives us the data or the documentation, it will say, hey, Travis, we got this great new part. This new part has all these E and P cores. Here's the thermal resistance, here's the power, and here's the temperature spec. We go in based upon that temperature spec, and it's typically TJ max, and we control off of that TJ max temperature to build the whole system. Now, there's a lot of confusion in the market because historically, from a temperature perspective, everybody in their head has it, hey, lower is better from a overall cooling perspective. But from a modern control with CPUs that can turbo, if typical power is 45 watts, but this part can go to 130 as an example under turbo, and that's just an example. It's not a specific value. What happens is you get very large delta T swings. So historically, where you were used to seeing temperatures in the 50 to 70 range, maybe up to 80, legacy 5-10 years ago, back to Haswell, pre-Haswell, now you're going to see temperatures that hug much closer to TJ max. And that's on purpose. It is to maximize performance at runtime. So temperature, TJ, means the junction temperature. It's literally the junction within the silicon itself. And they've got a bunch, and I'm not going to go into this because there's a bunch of sensors within the silicon, but basically that's what we control off of. That tells us, Dell, yep, you're doing a good job. I'm where I need to be. You're not overcooling, so we're not wasting it in space, form factor, and size. And yep, you're doing a good job from a performance perspective. Now, if we go beyond that, there is a ton of controls within the CPU itself that optimize based upon anything from an excursion standpoint. That's power, that's temperature. And I'd say Mark can go into this a little better than I can.
All right.
I love the handoffs.
Yeah, we'll work on that. We'll get it smoother by the time we're done. So actually, John, I sent you some visuals that we can show as we can talk through and help. And as Travis mentioned, right, like the old ways of doing things or the traditional methods and vocabularies that people use, like these have been around for a few decades. And what I'm showing here on this page, there's 2 different CPUs. On the left-hand side, we've got the Pentium 3 that was launched in 2001. It's just a single core. This particular product, this was back when we still had a discrete memory controller and a discrete I/O controller in the system. So we just had that single die sitting there. It was just one core with its cache. That ran at 29 watts. And so at that point in time, I don't even remember if we had turbo, or maybe we were just introducing turbo technologies at that point. So when you turn on the system, that CPU would go up to 29 watts and it would sit there, right? So we would design those systems to be only on the most extreme workloads that could fully consume that 29 watts would they be up at that 100 degrees or TJ max limit that Travis was mentioning, right? And that's what everybody was used to. So if you ran a workload that wasn't as demanding as the worst case workload that exists on the planet, you wouldn't be consuming the 29 watts, you'd be at something lower than that. So your average temperature would be less, right? Now on the right-hand side, I'm showing Alder Lake, and this was Alder Lake S. We launched it last year. This one is, if you notice, these two pictures are to scale. So we've got quite a bit more die size here. But I also am showing a power range, and that's 125 to 240 watts, right? That's how we're now showing or speccing our parts, is we're really embracing the dynamic frequency range that we have available, as well as what that means in terms of the power dissipation of the part. But if you go to the next page, what I'm showing that we have happening here is we took that single core, right? And now we have 8 of those cores on there, right? And you notice that core, the total area in the core, that shrank 90% over those 2 decades from all the process node improvements that we've had.
Wild looking, like actually
Right,
seeing it laid out that way. I don't think I've ever seen that kind of a breakdown before of how much, like if you look at what is it, like the one section of the memory is the size of the core was before.
Yeah.
Did we see this before? Because I don't remember seeing this image. Because like that's pretty impressive. I'm not gonna lie.
No, I mean, like I work here, and this is something that's in my head. Like I know that we've done, but it wasn't until I put this picture together, like, whoa, that's actually really cool, right? I mean, this is Moore's law in action right there. But when we shrink everything down, right, we still have one of those cores. If I just do the math simply, right, I've got 10 cores on there. I've got 8 big cores, and then I've got 2 clusters of small cores at the bottom, and we can talk about those in a little bit. But each of those cores, if I divide that 241 by 10, just to make the math easy, right, that's still 24 watts that I'm now putting into a much smaller area. And when I run workloads, I don't always run every single core simultaneously, right? So depending on how the software has been written, how many threads the software is taking advantage of or utilizing, I might actually assign a bunch of work just to a single core. So I'm going to run that core at the highest frequency I can in order to give the best performance. But that also means I've put a lot more power into a very small area.
Yeah.
Right. So now if you go to the next page, this is where we get into what Travis and I are actually doing on Friday nights. It's calculus. Math.
Yay.
Yes. Right. So this is what I'm showing is on the equation on the left for those that are really interested. Right. This is a simplification of the actual physics. Right. This is basically just a lumped capacitance model.
I like that this is the simplification.
Yeah, this is the easy one. But basically what it's saying is that the temperature response has an exponential aspect to it, right? So, and you see that over in the graph on the right. And what I'm showing on the right-hand side is the temperature response for different power levels for the same system, right? And the blue line, the power P, that was what we used to do traditionally, where we would design a system for let's say that 29 watts, right? And if you turned on the system, you started exercising the CPU, it would literally take tens of minutes before you would actually go up and saturate at that final temperature, the 100 degrees C. But when we started introducing turbo technology, and as we've expanded on that and expanded our dynamic frequency range, like we realized there's a lot of workloads that are a lot shorter in duration than that 100 or 200 seconds. Right. So let's take advantage of that. Let's push those cores to higher frequency levels. Let's get the work done faster. And this is where you start seeing the 1.25p is roughly 25% more power than what we had initially. Right. So those were the early days of turbo. And then as we've gone further, right now we go much higher power capability, more than the system can sustain. But you notice like the 4P, where I'm doing 4 times as much power as that system can sustain, I'm bumping into the temperature limit in a matter of seconds. Yeah. Right. And so this is what we're seeing now. And you see this especially on the mobile systems, where we're putting a lot more power into the CPU than the system can sustain indefinitely. So you're seeing, yeah, if I've got a high activity on a handful of the cores, my reported temperature, because we report the maximum on the CPU or the maximum on the die, is going to be close to that limit. But again, like, we have all the controls in place. We're not going to overshoot it. We'll reduce frequency as we need to. But it's all around making sure we're maximizing the performance and giving basically taking every last bit of margin out of the system and taking advantage of it.
And so if I'm understanding this the way you're explaining it too, is that because I feel like 100 degrees Celsius is always the big scary temperature when you hear about computers. Is everybody's like, oh, I hit 100, I hit 100. What you're saying is hitting 100 isn't necessarily a bad thing anymore. Maybe 5-10 years ago, it was a bad thing to be hitting that high. It's more about how long you're at that temperature.
It's how long you're at that temperature and what are you doing at that temperature, right? So when we're looking at our parts and we're designing them, we're expecting that the system cooling solution is working correctly, right? And so we would expect that when you're not running a heavy workload, the system cools itself down, right? And the CPU drops down in temperature. But we're also expecting, like, when you do run a workload, it's going to get warm. You're going to go to high voltage, high frequency, high power. The temperature is going to jump up. Now, I don't want to say stay at 100 degrees C all day long, right? That's not what I mean. But seeing the
it
temperature
peak to that isn't mean that something is wrong. It means that it's actually performing within the proper specifications.
Yeah.
Well, and John, that's what we designed too. So if you talk about these transient response, these PL2s, we actually go in and model. So what Mark is showing is basically a lump capacitance model. We do this so we know how much turbo we're going to get. So when we're doing the modeling of an experience, so let's say somebody opens World of Warcraft, we know that it's very heavy CPU intensive load for a short period of time while that application's loading. Then it pulls down. Once you're in game, there's a balance between CPU and GPU. Usually it's between 50 to 60% on the CPU, and you're closer to, if it's high res, 80, 90%, 100% on the GPU if it's discrete. So those type of approaches is how we control the system. But the way to think about this is the old way where we were just pushing, say, TDP or 45 watts into that mobile product, those are gone. We're now pushing 130 watts for maybe 3 seconds. Yeah. You will see the CPU jump 30 to 40 degrees. So if your idle's 50, you're at 80 within 1 second. You're approaching TJ max within, say, 3 seconds. That is proper design. So the old way where you saw 100, it's red, it's bad, those are gone. But if you're seeing 100 and let's say you're just watching a video, there's something wrong with the system.
Yeah.
That's a difference, right?
I'm going to interject here because I get a lot of questions in the DMs. We get a lot of questions on social media as well in Twitch chat itself. What do you think then is a target temperature that the system should be at if it's, say, idling compared to obviously doing a heavy task?
Yep. So if you saw CPU on Dell systems, usually you'll between 40 to 60, somewhere in that range at idle on the CPU. It could be a little lower, a little higher, depending on what the system is. But you have to be extremely careful. Background tasks running on that system. If you've got 12 Chrome browsers open, and let's say you're on a corporate system.
Only 12?
Okay.
I'm so impressed with how
you guys open Pandora's box. Let's talk about this.
Let's do 100 Chrome tabs.
Because I can tell you right now, I have over 100 tabs.
Okay.
And 2 windows at least.
Okay. 100 tabs, all this stuff running on the background. If a core is active, so Mark mentioned this earlier, I don't know if everybody caught on it. So if you had the 8 P cores and 2 clusters of the E cores, P is performance core, E is efficient core. Let's just assume that software is running on a P core. That one core can run at 28 watts. That's over 50% of a 45 watt TDP part, right? So if you talk about overall capability. So of that capability of that CPU, background task can pull heavy power. That is not idle. You are doing compute. And so from that perspective, if it's true idle, you're in that 50, 60 C range. If you're pulling power, like high power, you're going to be closer to TJ max. And so you can look at hardware info logs. So that's a freeware application you can look at and look at CPU power and look at temperature. That's a really good way to compare the information. But in general, what we've seen, if you're gaming, you absolutely, it is not wrong to hit TJ max and come down and balance it based upon turbo. If you're doing Cinebench, if you're doing any type of benchmarking on a CPU, it probably should hit TJ max if we've done our job right to maximize that performance. And I'll address something else because since we're on the topic, TCC offset, right? Doing temperature offsets. You are doing that based upon your control. You're governing your PC based upon the user's perception. From a Dell perspective, there is very little benefit of offsetting the temperature because you're giving up that performance for a little bit of temperature deltas. Now, what that does, it may give you a little bit of reliability difference over the long run, 7-10 years. But we design those systems to TJ Maxx. We design it within the workloads that we have. And every single component on that Dell system is tested to the max temp and max condition. So we go in and put thermocouples on every voltage regulator, every capacitor, and they're all ran at full workloads. I kind of ranted there. I apologize. Go ahead.
No, this is perfect. This is what we're here for.
What people want to hear. So thank you.
So then when we're so then you're talking about that. You're talking about like TCC offset. That's more of a comfort for me thing. If I want to control it, if I'm like, you know what, maybe my system, when you're talking about skin temperatures and stuff like that, you're like, maybe I'm slightly more sensitive to that. I want to lower the temperature. That's kind of a good way to give me that control over that again. If I don't like seeing that 100 degrees Celsius, maybe I'll turn it down to 95 or 90. And then my system, I may not be hitting as high of a performance, though, as you were kind of saying, some workloads it may not actually have any impact on.
That's right.
But it also just gives me a little bit more control. So it's less about less about getting performance changes and throttling and things like that. It's more just about a comfort level and a control for myself.
I'm going to put a marketing hat on and again, be super rude. In the show notes and in the description down below, we'll have information about how to enable TCC offset on your system as well.
Yeah, we have some videos that we can link to on that.
I wouldn't recommend it. Like if the system's designed to not need a TCC offset, I wouldn't go turn it on because you will cause the CPU to reduce frequency a little sooner than it would otherwise, right? So like, and
Travis is about to argue with them. I feel like this is
No,
happening.
no.
Fight.
We are bandwagoning on this, right? TCC offset was originally generated for skin temperature control.
Yeah, right. That makes complete sense.
If you go to the history of what TCC offset was, when we didn't have dedicated sensors on the board to say, hey, my keyboard's getting hot, what we did was we said, okay, I'm going to put a thermocouple on the board, and during development, we then correlated that said, when your CPU's 92, I know the keyboard at steady state's over spec, right? That was a legacy methodology to control T-skin. You can do it. Again, I think Mark and I are completely aligned here. You're just clipping the CPU performance for no reason. You can run up to 100. If you think you have a problem, look at power versus temperature. When your powers are less than 50% of TDP, it absolutely shouldn't be at TJ Maxx, right? If it's not a concurrent workload. That's an example of how our user base can look at their system and know they're getting a good design. But we know there's a lot of misinformation out there, and we're trying to get this fixed.
I think it's not even as much about misinformation. It's just old information that people just
old information. Yeah.
When I was building, I used to build PCs. That's what I did for a living, and that was always the case. If something was over 80, it was like, this is also a decade ago. Yeah, I was like, oh, okay, this is you want to sign
Something's
off.
wrong.
So now it's kind of different. We want to be seeing that, though. As you were explaining too, when you're stress testing the machine, if I'm running if I'm doing like AIDA64 or something like that on the system, this system may not be designed to run at max capacity for an hour while I do a stress test on it. So then you may see thermal throttling, things like that. But when you're talking about the different workloads we're optimizing for in games itself, seeing that 100 degrees shouldn't be as scary as it used to be. And as long as you're not seeing it and and you're not seeing stability issues as well. Like if you're hitting for too long and then all of a sudden blue screen, because we're trying to protect you from destroying your computer or having it catch on fire, then... Because the first PC I built did catch on fire. It was a fun story on that one. But I learned out those jumper cables. Yeah, those jumper cables can plug into anything on those old motherboards. It was like, oh, I'm missing a cable. Plug it in. Boom, lit on fire. So that was a fun time.
Okay, I really want to ask questions, but I'm going to keep professional.
Just real quick before you jump onto that, we've been using 100 degrees as our TJ Maxx in this conversation. The actual value is slightly different depending on which product. So go look up the specifications for your specific CPU. Some of them are at 105, some of them are at 100, some of them are at 95, 98. Right? We set that limit specifically for each SKU independently in order to make sure that we're doing the right things from a reliability and the longevity perspective. So we're using 100 right now because it's an easy number to throw around, but check your specific part.
That's good to know.
Yeah, that's really important, right? Because if you get out there and our customers say, I'm at 105, right? We're not saying 100 is the spec. Look up the part on, you can go to Intel Arc, right? And pull up their individual CPU. They can look at the CPU spec for that case. Just be aware, 100 is not scary. The key takeaway, if they take away anything, if you're under load, 100 is no longer scary. That is a control point. And we have multiple layers of control. The Intel CPU has its own control. Within Dell, we have something called over temperature protection. We have a separate diode on the board that we actually track for worst case conditions where we can take additional action. On top of that, there's something called dynamic tuning technology. If you guys look at the driver on the system, there's a lot of logic in there that we use to ensure that system is behaving properly. So you've got 3 to 4 layers of control, not including therm trip from Intel or their core features beyond that we do to ensure that, hey, if you put it on your blanket and you're playing a high-end game, if we go back to that previous case, it will behave appropriately and we will ensure that you do no harm, because there's multiple safety specs, IEC 62368. There's a UL 60950. All those they're regulatory specs for how that system must operate in those conditions.
And
so
then, go ahead.
Sorry, I'm going to continue to do it. Apologies. So we have a question about, what about thermal degradation?
Degradation.
Yeah.
Degradation.
There we go.
Oh my gosh, sorry.
You need more caffeine.
I do need more caffeine, and I will solve this.
So how does thermal degradation take?
Yes.
Are they
Take into
asking
effect on this?
generically? Because there's a couple different things that can degrade. In
I
this
think just
system, right?
generically, like when I'm running a system if a system is going up to 100 degrees, is that causing it to degrade faster, or should I be lowering it slower and it degrades, it'll last longer? Those kind of questions.
So in general, for the CPU, there's a couple things that come into play. One of them, or there's 3 really, right? There's temperature, there's voltage, and then there's the time that it spends at the temperature and at that voltage. So you need all 3 of those together in order to see degradation. And a lot of times we talk about degradation. Honestly, for most consumer applications, I don't think we're running the systems anywhere near hard enough to worry about it.
Yeah.
Right. Like the ones where you start seeing things are, where you're running that system for 5+ years in like some sort of embedded application where it's just running constantly flat out, almost 24/7. But I mean, everybody,
it's not really a concern at this, is what you're.
Yeah, for a consumer space, like unless you're doing something like you're constantly keeping the system vents blocked up, so that way even when you're not actively doing anything, the system's hot. Like,
so I shouldn't be running like 24/7 benchmarks on my Aurora back here, is what you're trying to say. If I do that for like 6 years, it might cause a problem.
Yeah.
So John, I mean, to that, right? If you look at all Dell products, mobile and desktop, we designed a 35C ambient. And so that's like 95 Fahrenheit.
So what does that mean when you say you were designing to an ambient temperature?
So our reliability testing, all the testing. So when we go in and we build these systems, we instrument everything, every single capacitor on the board, FET, all the stuff inside. We have a big bundle of temperature probes that we measure that at. From a test perspective, we test all products to 95 Fahrenheit. So you could be in your office at 95. That'll meet the full warranty of the Dell product for the life of the product, whatever that is. On top of that, we do reliability testing, and we don't talk about this much, but we go all the way to 40C ambient. And so 40 degrees Celsius, the external ambient in the room, and we will test all these products, and they go through our full reliability testing, and it's for months of testing or potentially multiple months of testing where we do long life testing on particular products. So all of those have been done to meet the warranty requirements to ensure that it's stable in those products that they get. On top of that, during tests, like when we develop products, we do 2,500 hours worth of testing on these individual systems. So if you look at combination of workloads, applications, and we look at the performance of that system during those workloads as well. So all of that is done based upon those configurations of the system with that CPU bursting to 100, right? Because that's the proper design control. That is done through our full development process. And usually from start to finish during development, it's a year-long process when we make a system. That's how we do that from a Dell production perspective.
And I guess that kind of goes ahead and changes a little bit as I cut off Anna again. And I think that kind of, a little bit highlights the difference between like the DIY versus the system. Like by doing that, I put on the marketing hat again, that lets us have a warranty on the system versus if I'm just grabbing parts all over the board. Yes, I can just throw fans into it or put in liquid nitrogen or build like a 6-foot tower and I can cool it however I want. But if any of those components aren't being cooled properly by having the fan blowing right over a specific regulator, things like that, it's different versus by doing that testing on the kind of like an all-in-one system that lets us offer like a warranty so that we know we expect reliability. Sure, there's part failures. That happens. It's impossible to control, but we have an idea that the majority of systems will be within that.
Yeah, there's a bell curve, and I got to be careful here on how much I can say, but basically we derate everything. So if you take a capacitor that's a 2,000 hour cap that's rated to 120C, typically you see a double of the life for every 5C reduction. So we will actually go in and we'll look at that individual capacitor. So the bulk capacitor is basically an energy storage device that may feed the CPU, as an example, through one of the rails. That little device, it's really sensitive, and you can see boards that have like exploded caps or
Pop
swollen caps, right? That's where that comes from. And so what's important there is we actually go in, we put a thermocouple on that cap. We will go run Prime 95 or Cinebench for a long period of time at 35C ambient. And then we will look at the temperature of that cap and say, you know what, that 2,000 hour cap needs to be 30,000 hours. And we will take that 120C spec and drop it to 95 as an example. And every single component on the board is basically measured in that methodology to ensure that when we give our products to our customers, we know that it's reliable. We've tested to the bounds. We've tested to that full ambient. Because in most cases, Mark was saying, hey, I know customers aren't pushing these to the edge. We're kind of saying the same thing on our part, saying, look, we test to 35C ambient. We've got reliability to 40C ambient. We do this on purpose to ensure that what they're getting is reliable. You will always have the bell curve, right? Maybe you got an excursion of 2 or 3%, right? Maybe the manufacturer, I can't say manufacturer, but say manufacturer had a bad part, right? That does happen at times. Yeah. But the test process at Dell is so rigorous and methodical. We do that so it's consistent. So when a customer gets a product, we know what they're getting and we know what those components should be operating at. And that's the difference between like DIY, right? Because DIY, I'm a DIY guy as well. I'm going to go slap a cold plate on one. I'm going to put these cool tubes, put an LED light. Am I going to instrument everything? Probably no. Even I won't do it because you're kind of lazy, right, at times. And I'll just put a big old fan and a bunch of stuff in it. And the sucker's this big by that point with a giant cooling tower.
Yeah.
You can do it, but it's not optimized, right? Because our mission from a Dell perspective is to give them optimized system designs with the control to control it how they want to. And that really is the TCC offset. It's our user selectable thermal tables. It's Alienware Command Center. We give them those options to tune it because we still want to give them that custom experience, but we want to do it based upon a default value of how we design that system.
And I can definitely say, I know if you go back to our YouTube channel, Umar actually did a video on our notebooks where they do drop tests. Not only do you guys do like thermal, but I'm not even kidding. He was dropping them from basically the ceiling and they were just fine.
You need to get a hold of Travis today.
Pounds of pressure too. Like he had a lot of fun, and I'm very sad I missed it. But I just saw a lot of comments in the chat talking about, they didn't realize that we do a lot of this kind of testing. It just shows that, we do care about what we're doing, and we're doing our very best to make sure the products that we have created, one, it's one that the community wants, but two, is something that we're proud of.
Yeah, the shock and vibration testing you're referring to, that is a lot of fun to watch in the high-speed videos of the systems. It's pretty interesting. Yeah, so years ago, we actually shipped sensors all around the world and tracked what is the acceleration as, like the different logistics companies like FedEx and UPS, I'll pick on them.
Oh, that's so interesting.
Right? Like as they're tossing the boxes around between trucks and in their distribution centers, like it's amazing how much of a beating it gets, and the amount of work that we do to design the packaging for the system, as well as the mechanical structures within the system itself in order to survive that. There's a lot of work that we do, but the testing is fun. The test videos.
To build on Mark's point, even just like airship, right? So as you airship, the temperature within the plane, it goes sub-freezing. And so all of these systems are tested from like 0 Celsius to 35C Celsius, right? So sub-freezing to 95 Fahrenheit. And we'll do shock testing where we take it in a chamber, it's setting at 40C, then we drop it straight down to another chamber and it's freezing. And so you'll have these different shock chambers that we do, but we do a ton of work on the reliability side.
That's awesome. And it's also reassuring too, because I used to redeem myself for my fire story earlier. I used to also do like custom cooling loops and things like that. And what it got to is like, I did it a lot. I'd come home as I got older, I have kids and things like that. My time that I have to spend tinkering on my computer starts dropping and dropping and dropping and dropping. So I'd come home and be like, oh, I want to play games for 2 hours. And then I would notice and be like, oh, that fan's not running right. Okay, I got to tweak that. My 2 hours to game is gone. So I'm like, okay, well, I'd spend it tweaking something. And it's nice knowing that, like, now someone else is doing those tweaks for me. Like, that's not for everybody. And some people just really love tweaking and playing and fiddling around with things like that. And there's no problems with that.
I want it to work.
Yeah, but then
I want it to open up and work.
Exactly. As I get older and have more children, that becomes more and more important to me, that I just have to work. I'm like, oh, I just want to play games, guys. I just want to play games and have time to do it.
Or mobile, right? I go to a LAN party with my buddies. I don't want to drag my whole, I mean, literally, I have a guy in our LAN party who takes his desktop.
I used to be that guy.
Straps, and he picks it up and he's got his monitor in one hand, right? I'll walk in with a 17-inch Alienware, and we're getting very similar performance, right?
I'm running this whole,
very capable.
I'm running
I did
this
that
stream.
at DreamHack.
Yeah.
Did that at DreamHack, streamed, competed, and everybody else had desktops, and I have this little 15-inch Alienware laptop, and everybody has to clean up, and I have a backpack, and I just slide it in.
Well, I'm running the stream off an X15 right now, and it's working flawlessly without any issues. So I know, it's exciting.
Hey, since we got Mark, maybe I can ask him a question. Where do you think the future challenges are?
Ooh.
The future challenges.
In other words, Travis wants to know what he should be expecting.
What should I prepare for?
Yeah, so there's a couple things that are coming. So some of them, like if we go way far in the future, our CEO Pat Gelsinger, he's announced some of our new process technologies that we have in place, and what we're seeing is there's a lot of movement towards stacking die together, which from a thermal perspective is very interesting. So again, right, that's all the work that the Intel side will be doing in order to provide Travis, here's what the new specs are, and make sure that it's something that can go into the system. But that does make things more interesting at the very local die level. The other thing that's coming, or that we started with Alder Lake, and Travis kind of pointed out to this a little bit when he mentioned the performance cores and the efficient cores, but having the different types of compute available on the SoC and really mapping the workload to the appropriate engine is going to be very interesting, I think, from a total energy efficiency and performance perspective, right? So we're beyond the time where it used to be just run everything flat out, right? There's workloads now that don't need the maximum frequency, but they need a good amount of performance on a regular basis, right? So things like what we're doing now, like we're just doing video conferencing, so my CPU needs to wake up and do something every now and then, but we're not talking any faster, the video is not playing any quicker, right? We just want a very consistent frame rate. So that kind of stuff I think is very interesting. There's a huge amount of work needed, not only from the CPU design side, but also the operating system side, and then also the actual software that's running on top of all of that to get all of those optimized and working together.
Yeah, we didn't even get a chance, and we won't have a chance today to talk about the software to CPU communication that has to happen, because I know Mark was mentioning that used to be measured in the seconds, but now the CPU is operating on the matter of milliseconds now. Yeah, which is
you know what? Right? I can solve this problem. So the questions, because we do have questions from not only the chat, but also that we didn't get to. I'll take blame for that. What if we, as a group, met together sometime in the next week or two? We'll do a Reddit thread. So we'll take the questions we haven't answered. We'll do a Reddit thread. So that way it'll live permanently, maybe online. Is that all right with you, John? This is your project. We won't set a timeline to it, but I think we would love if there are other questions. Maybe we'll do it on Discord, maybe Reddit. We'll figure out where we can do it. But I think there'll be another time that Travis and we can steal more of Travis and Mark's time, because I don't want to steal all of their time. Obviously, we like doing it, but they might not have the ability. So we won't announce anything yet about something coming up in the future there. But if there are a lot of questions, feel free to join our Discord server, discord.gg/Alienware. Post them in there. We can communicate back and forth. And if there's enough really good questions, we can dig that in and we can figure out there. But I think that probably comes to the end of our time, and I know Travis and Mark are super busy people, so I don't want to steal their time from designing systems and CPUs any longer. But is there any last thoughts you kind of wanted to leave us with before we sign off for the day?
Go ahead, Mark, and then I'll wrap it up.
All right. Yeah, so I need to set the bar high, right?
Yeah.
So all right. So no, I think we touched on a lot of good topics. Again, the way the CPUs operate today are very, very different from where it had been a couple decades ago, right? So the vocabularies that we're used to, the ways we used to look at computers and say, is this designed well thermally or not? Like that's changing, right? So like we've been introducing new ways of providing the specs for the Intel parts in order to really move the conversation and the vocabulary into the dynamic ranges that we operate within now. Getting everybody to learn about that, this is a fantastic opportunity, and so I thank you for the time, and hopefully we provided some education and
Definitely
people
did.
learned something from this.
Awesome, thanks.
Yeah, I think I would just parrot that. So I think the key takeaway, I think, for the audience is just realize if the system's operating at 100C, that is probably typical operation for gaming. From a Dell perspective, we put a lot of heart and work into the products to ensure that they meet specification. Obviously, look at the parts themselves, understand what's going on. And obviously, if from an overall product perspective, we love the feedback. So give us feedback through this forum. We'll take it. We'll try to get your questions answered. But, appreciate the time, and hopefully we provided some insight to the community.
Constructive feedback, though.
I like all feedback. So
all feedback.
Well, thank you again, guys.
Awesome.
Like John said, your time is valuable. We appreciate it, especially Travis. You're now the internal celebrity that we have ever since your PC debut.
I knew I should have said no to that one. Yeah.
No, you're
was great
sucked in for
then,
life
yeah.
now. So that was great, and that was one of the touch points of why we started doing this, is because of your guys' insight. So again, thank you so much for your time.
No problem.
Awesome.
Appreciate that.
You're welcome.
Thanks everybody
Have a
who
good one.
tuned in as well for joining us.
Yes.
You can always find out. We'll have the VOD up on Twitch soon, and then we'll have the video up on YouTube as quickly as we can as well. Again, as I said, if you have any other questions, feel free to leave. We're always watching Reddit, reddit.com/r/Alienware, discord.gg/Alienware. Yeah, there's an exclamation mark in chat. Or join us on alienwarearena.com. I'm always there watching everything, so you can join us there and ask questions in the forums too. So thanks everybody for joining, and can't wait till we can do another one of these, and we'll see you guys all later. Bye, everybody.
Bye, guys.
All right, thank you.
Bye.